Hi everybody, today we're going to solve the one period binomial option pricing model. Okay, so again, what is the one period binomial option pricing model? So at t equals 0, we have a stock here, it has initial value s0. At t equals 1, it only has two possibilities, either it goes down, up or down to, like, let's say 107, maybe this is $100, or down to 93.46 with probability p, with probability 1 minus p. And we're trying to price a call option or a put option on this stock movement, right? So last time we looked at maybe looking at the expected payoffs. So if the strike price is 102, then the expected payoffs would be 5 and then 0 because we don't exercise the option if it goes below the strike price. And then we know what p and 1 minus p is, and then finding the expected value, and then because it's a binomial distribution, it's easy to calculate the probabilities of ending up in each of the spaces, and and then possibly applying a utility function, because I think as we went over last time, it's sort of confusing. You might be risk averse, so maybe you don't care that much about winning a lot versus losing, right? However, it turns out we actually don't need any of this sort of expected value stuff. It turns out we can construct a replicating portfolio. So let me write that down. Replicating portfolio. So let me give you the two options for a replicating portfolio. Number one, buy X units of the stock at time equals 0. Because again, we're constructing a portfolio based on time equals 0. We're making some decisions at time equals 0, and they will pay off somehow in the future. Okay, and then we can also buy Y dollars of a cash account. Cash account. Okay, so how do we construct a replicating portfolio? So our assumption here is that using these two, or like our lead, right, is that using these two methods, we can actually construct something which gives us the exact payoff to the option would, okay? And if we're able to price this more simple model of just these two actions, then we'll have an exact price for the option because they give the exact same payoff. Therefore, the price of the option should be exactly equal to the price of this very simple replicating portfolio. So how much money do we actually earn at t equals 1? Well, it's very straightforward. It's 107. So there's two possibilities. Either the stock went up or went down, right? In possibility 1 here, okay, 107 times x plus ry, so y has increased because of the interest rate, is equal to 5. Or the other option, okay, 93.46 x plus ry is equal to 0, okay? So then we can solve this and get, let me get the numbers, and get x is 0.3693, y is equal to minus 34.1708. So what does this mean? This means we can replicate the option payout by buying 0.3693 units of the stock at time equals 0 and borrowing negative $34.1708 from a cash account, okay? And then later at t equals 1, we have to pay back r times y, and then we have to pay back we get, because we bought the stock, some payout here, and our choice of decisions should exactly replicate the possibilities of the option payout, okay? So then what should the price of this option be? Well, the price of the option should be the price of the replicating portfolio because they lead to the same payout, and the price of the replicating portfolio should be 100, because we're buying the stock at time equals 0, 100 times 0.3693, okay, minus 34.1708, which is the money you put into the cash account, which should be equal to $2.76. Okay, so the fair price for this option is $2.76. I will say something that's interesting is, notice here in this system, we never used the price, or we never use a probability p, okay? What does this mean? This means that the price of these, I'm going to draw two possible stocks. So here we have one stock. It goes up to 107, and then down 93.46 with probability 99%. So here 0.99, and then 0.01. Or here's another stock. It goes up to 107, down to 93.46, but the probabilities are different. I'm going to flip them, 0.01 and 0.99. Okay. It turns out, according to this theory that we just proposed, the price of these options should be exactly the same, even though the probability of you getting a payout here is like way better, you know. I think the professor just kind of leaves it as a question and then later answers it. So I'll do the same. I'll just answer it later what the professor said about this. But yeah, it's weird how both these options have the same price, because we never, in our argument here, we never used the value of P anywhere. Okay. Finally, I want to solve this using abstract numbers. So here we have S0. It goes up with probability P, and it goes down with probability 1 minus P. And then here, the payout is CU. And then here, the probability, the payout is CD. Okay. And then the price of the stock here is U times S0. And here, the price of the stock is D times S0, where U is greater than D. Okay, so this is our we won situation, and here is our we lost situation. And then we have a strike price, or we don't even have a strike price here because we just have this arbitrary payout. This is a constant, but it's arbitrary. So this works both for call put options, because in put options the CD would be non-zero and CU would be 0, or at least something like that. So again, what does this look like? We're trying to construct a replicating portfolio to replicate the output of this option, right? So at time equals 1, so we bought some stock. We bought X units of the stock at S0, we bought X units of the stock, and now at time equals 1, it's worth U times S0, okay? Then we put some money into the cash account, RY is equal to CU, okay? And then we have D S0X plus RY is CD, okay? So that's our replicating portfolio. Again, we can solve this, and I'm actually going to solve it now. So let's take this and subtract this, and we end up with U minus D S0X is equal to CU minus CD. And we end up with X is CU minus CD divided by S0 U minus D. Okay, so now let's solve for Y. I'm going to add them instead together, and we end up with U plus D S0X plus 2RY is equal to CU plus CD. And then moving everything to the other side, we go CU plus CD divided by 1 over 2R U plus D S0. Did I do that right? No, I did not. 1 over 2R, sorry, here, minus U plus D S0X. Okay. So now I'm going to put in X here, and the S0 cancels out up here, and we end up with 1 over 2R CU plus CD, and then let's see, minus U plus D, and then we have CU minus CD over U minus D. That's correct. Okay. And then in order to make this sort of multiply out, I need to multiply both of these by 1 minus D, right? And so we end up with CU U plus CDU minus CUD minus CDD, and then I multiply this out here, and I get, let's see, minus CUU, let's see, plus UCD minus CUU plus CDD. I think that's correct. So then this cancels out. Okay. For some reason I put this here, CDU, just to make sure. Yeah, I'm just gonna put this here just to avoid mistake. So this, there's two of these, so we're adding them together. Then CDD cancels out with CDD, and there's two of CUD, CUU. Yeah, it's possible I might have, yeah, I think this is a D here. Yeah, so we end up with y is 1 over 2r T2CDU minus 2CUD, and then the 2 goes away, and we just end up with that. That's what y is, okay? So then what is the price for this replicating portfolio? It should be S0, x plus y, okay? So let's take that, the S0 cancels up there, and we end up with CU minus CD divided by U minus D, CU, okay? And then we add y to this, so plus 1 over R CDU minus CUD, okay? So then in order to, so let's put it together now, 1 over, let's take out the 1 over R in front, and then we end up with, so we're multiplying. So here's how I'm going to collect terms later. Yeah, so CU minus CD, so this will be R minus probably D over U minus D CU plus whatever, I think it's like U minus R. Yeah, U minus R over U minus D CD. Okay, so that's the price of our replicating portfolio, and that's our option. Okay, and this is independent both of Q, it's independent of, I mean, it's not independent, but it does depend on price and of CU and CD, but CU and CD can be any constant. So that's also interesting. The only thing it really seems to depend on is this U, D, and R. Okay, so now I also want to convince you that R is actually between U and D. Okay, so how do I do that? Well, it's very straightforward. It's sort of an arbitrage argument. So if R, so suppose R is, for the sake of contradiction, that R is less than U is less than D. Okay, then what you should probably do is you should borrow as much money you can from a cash account, so like Y dollars, a lot of Y, okay, and then buy the stock, buy S0. So then what happens at T equals 1? Again, let me draw it out. So here, so there's, so this will be U S0, and then D S0. And so somehow this RS0 is down here. Okay, so if this is the case, right, we borrowed lots of Y, we buy the stock, and then in any scenario, right, in both of these scenarios, since both U and D are bigger than R, then we actually make money, and it's risk-free, right? There's no, we always make money, right? So again, no free lunch, whatever arbitrage that we talk about. In all cases, we actually, there's the professor introduces a new idea of arbitrage, where it's saying that now we're working in a probabilistic space, and something has arbitrage if the price that you pay for it is less than or equal to 0, or you don't get paid. However, at time equals 1 or at a future time, like you get positive cash flows, right? Or there's at least one situation, random variable situation, where the cash flow is positive. Okay. So basically, he's trying to extend it to probabilistic space. But yeah, in this example, right, if R is less than U is less than D, then we can just borrow, buy the stock, and in both cases, we'll make profit, right? Okay. And then very similar argument the other direction. So suppose this, right? Then it's probably best you can short sell the stock, then take the money that you got from short selling it, S0 times X or whatever, and put it all into the cash account. And then because the cash account is better than, it's a good idea to put money, the cash account is more like powerful than just buying the stock. So then later at the time, since the cash account has grown more than the stock has possibly grown, then you get money, like free money, right? Therefore, it is known that R has to be between these two values. So let me go back to this thing here. If R is between U and D, okay, then this is positive. This is positive because U is bigger than D. This is positive, and this is positive. And you can actually, let's call this Q star, and let's call this, it turns out that 1 minus this, so let me do this. So we have Q star is this, R minus D over U minus D, okay? So then 1 minus Q star is 1 minus R minus D over U minus D, okay? And so then we have here U minus D minus R plus D over U minus D. The D's cancel out and we end up with U minus R. So 1 minus Q star is equal to this, okay? So they're actually like up, they sum up to 1 is what I'm trying to say. So we can treat this as a new probability measure, okay? New probability measure Q, okay? So then we can sort of like rewrite this expression as 1 over R and then expected value given this new probability measure Q of the cash flows at 1. Okay? So what is this Q? This is known as the risk, I think it's called, let me check.
So in particular was the...
Okay, risk neutral pricing. Just had to make sure I have the right word for it. Risk neutral pricing. So why is it risk neutral? Because the way we've calculated this is by constructing a replicating portfolio, which is actually just risk-free, right? We bought the stock, we know where it's going, and then we put money into a cash account, and that's why it's risk neutral, right? There's no like options, but this is how we somehow ended up on the prices of this option. Okay, using this new sort of probability measure, right? And these U and R, again, they are based on the direction that the stock has gone in, right? S0 times U, and then D times S0. Okay. Yeah, so this is finally the solution to the one period binomial option pricing model. Next time, we'll look at multi-period. Thanks for listening. See you next time.